smaller subset, and this one is specifically about neural networks. So this is what we're going to focus on today. And deep learning has like a couple of features. So it's like computationally intensive. It also requires like more power. Like a lot of times you might want to use like GPUs to train like deep learning models rather than like CPUs. There's like less theoretical guarantees. Usually like when you get like a new architectural model, it actually comes out like maybe like 5 years before like the theory catches up. So this is like how it is right now. And also we have like empirical decisions based on like numbers, and it's nonlinear, non-convex. So there's like, you might like converge on like a local min or like a saddle point. You don't always converge on like a global min. Like that's pretty unlikely. And also it's like very data hungry. You need like a lot of data to train, because like the model, it's like a very complex model. It can definitely overfit. So definitely need like a lot of data for it. So this is going to be like the overview. We have like a couple of topics we do want to cover. So this is going to be one of the longer lectures. So I hope if you have any questions in the middle, just raise your hand. So first we'll talk about like the perceptron, which is like the main like building block of like a neural network. So it looks like this. It takes in like the inputs like x1, x2, x3, and up to xn. And then it has like weights, so each weight gets multiplied by the input. So like weight 1 gets multiplied by the input 1, weight 2 gets multiplied by input 2, and then like so on. And then the bias b gets multiplied by like 1. So it's like a value that you can just like adjust up and down, and doesn't actually depend on any like input. So that's why it's 1. And then the x's, remember, they're like just numbers. So like just any number, and then w is also like a scalar. So it's the sum of the weights plus times the inputs, and then plus the bias. And then so this is really similar to what we did with like machine learning in like unit 1, right? Like we have like weights multiplied by the inputs. And then, however, we do have like an activation function here. So this one is like a binary step function. So basically, if the output is greater than 1, we'll just output 1. If the output is like less than 1, we'll just like output 0. So this will like constrain our output to like a 0, 1. This is like just one of the many activation functions we can use, but this is like one of the most simplest, like most like easy to understand activation function, right? Like if it's just like negative, we get 0. If it's positive, it gets 1, right? So yeah, this is like really similar to linear regression, but we do have like an activation function. So let's look at like what a perceptron can do. So we can like linearly separate data. So if the data is linearly separable, meaning like we can draw a line that separates like class 1 from like class 0, we can like make a perceptron that learns the function. So like look at and. So like if either the I1 or I2 is like 1, then like it's like black. If both, that was the one. Sorry. If both are 1, then it's white. Otherwise, it's black. So that's and. And as you can see, like we can just fit our perceptron to just like separate the data perfectly. So we have like all the ones with black on one side, all the ones with white on the other side. This is or. This is like if one of the inputs is 1, then it will be white, and otherwise it will be black. And we can see it's also linearly separable. However, look at like XOR, for example. Like how will we linearly separate XOR, right? Like there's no way to draw a line that like separates both the classes, right? Like there's no way to like make a line that like white is on one side, whereas like black is like on the other side. So XOR is actually one of the functions that a perceptron cannot learn. So it's not a linear function. So we need to get a bit more complex than just a perceptron. So yeah, also a perceptron is pretty similar to a neural network in some ways. Not a neural network, a biological neuron, like a brain. So in a biological neuron, we have dendrites that take in like outputs from other neurons, and then it goes to the axon, and then like it'll like either fire or not. If it fires, it'll go all the way down, and then the action potential will like reach the synapses and like propagate to like the other neurons. So pretty similar to what we learned last week on neuroanatomy. So yeah, this one also like if you can make like a network of neurons in a brain, and like the brain has like trillions of these. So this is why we want to take inspiration from the brain. Okay, so now let's talk about neural networks, which is the more complex version of a perceptron. So this is what a neural network looks like. It would be nice if you just look at this and remember what this looks like. So we have layers of perceptrons, basically, and then each perceptron takes the inputs from the previous layer, and then it decides like what to output, and then its output would go on to every neuron in the next layer. So, and then if we stack multiple layers, we'll have like an input, then we would have like some hidden layers that the data goes through, and then finally we'll go to the output layer. Okay, any questions so far? We're good? Okay, cool. So what is it? Like, what does it do, right? It's basically a data-based function approximator. What does that mean? It means that we give it a bunch of data, and it learns to approximate the true function that's generated from like the real distribution. So let's take a simple example. So up here we have we want to find like m and b in like a linear problem, right? Like y hat equals mx plus b, right? And we just want to approximate like the true distribution using like a linear fit, right? So that's like the most basic form. And turns out you can also do that with cat pictures. You can also classify between cats and dogs. So we'll look at how we can do that. So let's talk about what was there before deep learning. So this was a pretty cool article about a Japanese AI company that was trying to classify different pastries, and they had so many steps. You had to have a pipeline of algorithms in order to get to the final classification. You had to make an algorithm that separates different breads. You had to there was one algorithm that looked at how baked the bread was, how brown it was. It had to determine what lighting it was under. It was a lot of things. And I like that this last sentence, they spent 5 years just immersed in bread just to make this this thing that recognized different breads. So that was before deep learning. And after deep learning, I believe things have gotten a lot easier. So we can just give it a bunch of data, and then it just learns by itself, and then it can just output what we want. So this is why deep learning is powerful, and this is why we use that all the time these days. Okay, any questions? Okay, we'll go on to forward propagation, which is how we how we calculate compute how the neural network gives us the outputs. So yeah, let's go over that. So let's talk about this part, which is in between two layers. What is going on with the weights? So our weights for this layer, we can represent it as a matrix. So the inputs, right, is 4 elements, and the output we want 5 elements, right? So you can see that the goal for this layer is a 5x1 vector. The data we have is a 4x1 vector. And in order to compute this, we first do a matrix multiplication. So the weights are stored in a 5x4 matrix. So because you can see we have 4 in the input, 5 in the output. So 4 times 5 is the number of weights that we have. So we would use a matrix multiplication to compute the output. So let's start with that. So how do we do matrix multiplication? We multiply each square of the input with the square under it. So basically, we take the data, we do this to it, like we flip it like 9 degrees, you can think of it, and then like you multiply each element like this way, and then you get like this. So this is like the sum of the first element in W multiplied by the first element in the input, and then the second element in W multiplied by the second element in W in the data, sorry, and then the third element in W multiplied by the third element in the data, and finally the fourth element in W multiplied by the fourth element in the data. And then we just take the sum of that. So that will give us the first element. And then we do that again. So multiply. Now we're using the second row of W. And then we do that again, again, and again. So this is how we do like the first step, which is like a matrix multiplication. And then we will actually apply what's called an activation function. So previously we talked about like the binary activation function, right? If it's less than 0, we give it 0. If it's greater than 0, we give it 1. Well, in this case, it's a bit different in that it's like a smoother function. So right here, it's sigmoid equals 1 over e to the negative x. What it does is it also clamps the outputs between 0 and 1. But it's like a smooth function rather than like a step function. And it turns out later on, like this function is better for computing like the loss and the gradients in order to like update the weights. But we'll talk about that later. But this is what you need to know. Like we just apply the sigmoid activation function, and then we finally get the outputs of the first layer. I guess does anyone have questions at this point? Good? Awesome. Okay, so basically this is like the summary of what we did. We took the data, we took the weights, we did like a matrix multiplication, and then we applied the activation function, and we get the output of the first layer. Okay, now this is what we just did, right? But we have how many layers? 1, 2, 3. Well, we have 2 hidden layers and 1 output layer, so we'll do that like 3 more times. So just like that, and then we'll get the output. Cool? Okay. Now let's talk about how are we going to use the output layers. The output is just a bunch of numbers at this point. How is it going to classify it as like a cat or a dog, right? Like how are we going to interpret these numbers? Well, in this case, we're going to use what's called the softmax activation. So what it is the sum of the exponential, that's the exponential over the sum of all the exponential. And what that does is it takes the inputs, right, and it clamps it such that the sum, it sums to 1. So we can use these as probabilities now. So we can take like, say like the first output as like the probability that the input was a cat, and then we can take like the second output like the probability that the input was a dog. And since all these numbers, they sum to 1, we can definitely just use them like probabilities. Cool. Any questions? Oh, yes?
How do you know which one is the cat and which one is the dog?
We are going to be the ones that design this. So if we designate like the first class, like class 0 to be dog, then class 0 will be dog. And if class 1 will be cat, then like we can choose. But it doesn't matter. It doesn't really matter, but we have to be consistent when we compute the loss. Any other questions? Okay, we'll continue. Okay, so quick question. So why do we need to use an activation function? Well, this is because we want to model a non-linear function. So remember the perceptron, right? That was like a linear function, right? Like that can only model linear relationships. What happens if we don't use an activation function? Well, look at what happens. If we don't have an activation function, we can just directly multiply the next layer's weights by the outputs of the first layer, right? And the first layer was just the matrix multiplication without the activation function, right? And since matrix multiplication is associative, meaning like you can compute like either wx first and then compute w, the outside wx, or you can like just do w of I plus 1 times wi and then multiply it by x. You can see how like this wi plus 1 wi, right? That we can also just write as a matrix. So that'll just be one matrix multiplication, and that'll just make it a linear function. So that is very unfortunate because then our neural network will not be able to model anything that's nonlinear. Any questions? Okay, we'll continue. Okay, so there's more activations functions out there. Usually we use ReLU since it's pretty easy to compute. It's just the max of either like x or 0. But there's also some other like activation functions that we can use. We went over the sigmoid, which is the one that we use for our example, but there's also tanh. It's different because it's like from 1 to -1 rather than from 0 to 1. There's also leaky ReLU, since you can see how the problem with ReLU is that when we're like less than 0, right, it just clamps it to 0, and the derivative is 0, right? So you don't know which way to go. Like, even if you increase x, it will stay at the same value. So that's why we've also come up with like leaky ReLU, which is there's still going to be a tiny bit of slope when we're less than 0. And then there's also max out, and there's also ELU. This one's kind of cool because it's like smooth. And yeah. Okay, now we're going to go on to backpropagation, which is how the neural network actually learns. So we previously talked about how the neural network computes an output, but how do we like learn based on data? Like if it's like wrong, how do we like correct its mistakes? So let's start with let's talk about like what we want to do, right? We want to find the optimal W matrices such that our output will exactly like model, like if we passed in a cat image, it'll give us a cat. If we give it like a dog image, it'll give us like the second neuron, like second output neuron that'll be like activated, right? So ideally, if we had like the right W's, then the problem will be solved. But how do we compute the W's, right? Well, this is why we use backpropagation. So first though, we need like a metric to say how bad is our model. In this case, we're going to use what's called cross-entropy loss. So how do you compute cross-entropy loss? We take the outputs of the untrained neural network. It might be a bit hard to see, but it's 0.2, 0.2, 0.4, 0.1, and 0.1. That's like the output like after softmax of our neural network. And then we also have like the actual like y values that is from our data set. Like we labeled our data set, so we do have the answers to our problem. And we actually want to see that it's a cat. So we want cat to be 1, and then all the others to be 0. Does that make sense so far? So this is our output. This is what we want to see. Now what we can do is we can take what we want to see, we multiply it by the log of what we have, and then we sum all of them, and we negate them. So it's basically the negative sum of the true outputs multiplied by the log of our predicted outputs. Now, why do we want to use the log? That's a great question, and should we go over that? Like, why want to use the log? Sure. So because the log, so you can look at the wait, how do can I raise one of them, or actually sorry. Yeah, can I draw?
Yes.
Okay, cool.
Okay, that works. I was gonna choose
Awesome.
on the screen.
I did not know you can do it there. Okay.
You can just draw.
Okay, cool. So remember what the log function looks like? It's like this, right? And it's 0 when x equals 1. So this is 1. So like this, right? So this is a log function. However, we want the negative log. So the negative log looks like this. This is the negative log. Can everyone see this? Okay, cool. This is the negation of this. So it'll just look like something like this. Ooh. Actually, sorry. Log. Negative log of x. And that will give us something like this. Wait, yeah. This one. So we don't actually care about this because our x is always bounded between 0 and 1. But if it's like far from 1, like if it's like, oh, by the way, our true output is always going to be 1 or 0, and there's always going to be 1, 1. So we only care about this, actually the only one where the output is 1. We don't care about the other computations. So let's just focus on like the first one, right? Like the first one is the true value has to be 1. So this log is like positive. And then it's 0.2, right? So it's like right here, right? If it's far from 1, we give it like a high loss. We tell the model it's really bad. But if it's like closer to 1, you can see how like as it gets closer to 1, the loss slows down. So that's actually why we use the log. It just helps us with like approximately like this kind of smoothness. Does that make sense at all? Any questions? Very cool. I think we can continue then. Okay. So let's continue. So we actually don't compute the loss over each sample. We actually compute the average loss over many samples over like a batch of samples. So what we do is we compute the loss of like one element, and then the batch is just the mean of the loss. Does that make sense? We just use the batch. Okay. And yeah, we can just average over many little cat and dogs. Okay, now let's go into like the gradient. So what the gradient basically is we want to see how much the output changes if we change an input, right? So let's start with like partial derivatives, right? The partial over partial w of wx is just x, right? That just means like if I modify w by some amount, if we modify w by 1, wx will change by 1, right? Okay, now what if we want to compute that on a vector? So capital W is a vector. And we're computing the gradients over w1 x1 plus w2 x2 plus dot 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 plus wn xn. What that means is, what is the change in the output if I modify each element of w? So we get like a vector as the output. So x1 would correspond to like the derivative of the derivative of the output with respect to w1. This would correspond to the derivative of the output with respect to w2, and like all the way down to wn, right? So that's the gradient. It's just like a vector form of the derivative. Does that make sense? Cool. Okay, now we want to compute the gradient of all the weights. We want to compute the gradient of the loss with respect to all the weights. So the loss, the gradient of the loss, which previously we computed was like the negative sum of the true times the log of the predicted, right? The gradient of that turns out to be just the predicted minus the true value. It's a very simple output, but the derivation is kind of long, but I do have like a link to it. So that's the gradient of the loss with respect to our neural network like outputs before softmax. Now we can compute how much does the loss change with respect to each w. So wij here is the weight for the jth inputs, to jth weights for the ith neuron. Okay, does that make sense? And then we want to compute the loss with respect to that. So we have, we can use the chain rule. So remember the chain rule is like, you can have the partial loss over partial of the outputs times the partial output over partial of the weights. Okay? So that's just the chain rule. And then we can just sub in the values, right? We know from, we know partial loss over partial xi, that was just that, right? X minus y, so xi minus yi for like the ith element of x and the ith element of y. And then the partial xi with respect to partial wi, that's, remember that was, we had something like wi, like the xj n minus 1, right? That was like how much we multiply the weight by the output of the previous layer, right? So previous outputs. So the derivative with respect to the weight would just be the value in the output of the previous layer. Does that make sense? So this would be like for the last layer, like for each element of each weight of the last layer. This is how much the loss changes if we change the last layer by some amount. We're doing it for each of them. Any questions? I know this is like a bit confusing probably. Okay, well, you guys are all very smart then. Okay, so you can see how like the gradient would flow backwards, right? So we have the loss with respect to like the output of this. We can use that value to compute the loss with respect to the weight of the last layer. And then we can also use this value to compute the loss with respect to the layer before, like the output of the layer before. And we can use that via the chain rule to compute that. And then on until we get to like the layer, the weights of the first layer. Right, so this just shows you like you can compute the gradient with respect to all the weights. So remember like the gradient was, wait, nope. Remember that the gradient, like we could compute the gradient with respect to like w of like some function, right? The sum function here is the entire neural network. And we're computing how much the loss changes with respect to each, like all of the weights. So like all the weight matrices. Okay? Does this make sense?
Maybe raise your hands if it makes sense.
Okay, does this not make sense? Oh, this does not make sense. Okay, what part do you want to like go over? Oh, yeah. Why does it flow backwards? That's a great question. So remember the chain rule, right? So we start with like, we know how much the loss changes with respect to the last layer, right? That was like this kind of computation, right? And now that we know how much the loss changes with respect to the last layer, we can compute how much the loss changes with respect to like a previous layer, right? And we can compute that using what we computed for the last layer, using the chain rule. Does that make sense?
So we are like examine which layer is causing the problems.
Not exactly problem, but like how much the loss changes. We want to minimize the loss, right? So we want to see how much, if I tune this, like if I move this here, how much the loss will change, right? For each weight. Like if I change this weight, how much will the output change?
So what we're gonna use for the output, like if we get the loss.
Yes, we get the loss, which is how bad our model is, like how far off our model is from what we want, right? And we want to get that down, right? Because we want to get the loss as low as possible. If the loss is low, then it means our model is very accurate.
Okay, thank you so much.
Does that make sense?
Yeah.
Okay, cool, awesome. Any other questions? Or any, sure.
I mean, I'm kind of confused. Like, is it basically like you're taking like a function of loss
Yes.
with respect to weights, and then you're taking derivatives to see how you could minimize it?
Exactly, yes. So you want to see like for each weight, how much the loss will like increase or decrease if I increase or decrease this one weight. And then we we can compute like a vector of all the weights, like how much does the loss change with respect to all with each of the weights. So we get like a vector as like the output. Like
It's really like multiple gradient.
it's a big gradient. Yes, it's the gradient of like the entire neural network plus the loss with respect to all the weights of the neural network. Yes.
What are we supposed to do with this information?
I'll get to that. Yes.
Yeah, so is W a matrix, and then is like
Mhm.
n the number of data points, or like what?
Oh, sorry. Yes. In this notation, n is the layer number, so like the last layer, right? N is like number of layers. Wij is the ith neuron. No, so the jth weight in the ith neuron. Okay, and then like this is like one element in like the matrix for the last layer. Does that make sense?
Okay, so n is like the number of layers. That you
Yeah.
have.
That's yeah. Any other questions or confusions or? We're good? Awesome. Okay, cool. So now why do we want to use this, right? Well, we can update our weights using the gradients. We can do the new weight equals the old weight plus the learning rate multiplied by the gradient, right? So if the gradient was like big and positive, then we want to make it like, we want to like subtract that from like the old weight, like subtract a lot. If it was small, we can subtract a little bit. If the gradient was actually negative, then we want to add a bit. And if it's like very negative, we want to add a lot. So, and do you know why we want to do minus lambda rather than plus lambda? Does anyone know? Yes.
Because we're trying to descend the loss landscape.
Yes.
So we're trying to find the global minimum.
Yes, we want to go down. We don't want to go up. We want to minimize the loss. Exactly. Questions? Okay. Awesome. Let's continue then. So now, how do we compute lambda, right? Well, I'm not going to talk about how we compute lambda, but if lambda was too big, right, you can see that like on the right here, right? We might just jump out of the loss landscape, right? We just get farther and farther and like diverge. If it was high, it might like settle around like a neighborhood of like the minimum, but not actually get to the minimum. And then if it was like too low, it'll just be super slow. Like it'll just take a lot of iterations to get to the minimum. So we want to find like a good learning rate that's like both like pretty fast and also like doesn't like jump out of like diverge, right? So you can see like this graph here. If it's too high, the loss curve with respect to like the epoch, which is like the number of iterations we do with this gradient descent. Like if it was like too high, it'll just diverge. If it was high, it might like settle around like some value. If it was like too low, it'll just like be super slow. And finally, if it was like a good learning rate, it'll just go down and it'll be what we want, right? Yes.
Does the learning rate have to stay consistent the entire time? Or can you go like down?
Yes, actually, that's a great point. There's learning rate annealing, which means you can you can schedule your learning rate. And actually, when you're doing like your project for this week, I believe